So we're attempting to explain a better model for the atom. Instead of Bohr's model of the atom, or our planetary model, where we have a nucleus and electrons that zoom around in orbitals around our nucleus, we're going to try to understand ways that we knew, or ways that we found out that a better model exists. Okay, and the first way that we kind of realized this was by realizing that electrons, they interfere with each other the same way light interferes with other wavelengths of light, or whether other photons of electromagnetic energy. If you have two wavelengths of electromagnetic energy that can interact constructively, then the frequency will be augmented, or the amplitude, sorry, will be augmented. But there is also a way to have them interfere with each other in that they destructively decrease the magnitude, or the amplification, and the light disappears. This is true of light waves and sound waves. Okay? And we have an experiment where we tried to see if electrons interfered with each other destructively or constructively. And let's watch this video here.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the sound. If we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematics...
Okay, so that's enough of that. What do you think? What's that all mean?
I don't know. Why are we watching that?
Well, what we're trying to see is that the electron is not behaving like our model of a little tiny piece of matter, right? Well, it does in some ways, but in other ways, it behaves more so like a wave, like electromagnetic energy. And so we say on a quantum level, which is, really tiny level, when you get really, really tiny pieces of mass, they're so close in terms of energy to that of electromagnetic energy that they're almost as if they are actual electrical potential of energy, electromagnetic energy. So electrons can be characterized as particles like this and answer lots of questions. But other questions, if we want to answer them, we have to begin to characterize electrons not as particles, but as waves of electromagnetic energy or waves of light. Okay? Now, waves of light, we can think of waves of light traveling from the sun all the way to Earth. And these kind of waves we call traveling waves. But an electron isn't a traveling wave, but it's what we call a standing wave. And it's kind of like a wave that you would think of a guitar string making when you pluck that guitar string. All right? You can pluck a guitar string or any string that's fixed at its ends, and depending on how hard you pluck it, you'll see one of these patterns, right? And you're not limited. You can see this one, this one, this one, or this one. But you won't see something in between, all right? So essentially, it's like we have our quantization, right? It's quantized. The energy of the electron can have a value of n equals 1, 2, 3, or 4, but the energy is released in one of these ways. So again, it's behaving like a standing wave. Now, the electron is not a one-dimensional wave. This is kind of like a one-dimensional wave. It's either going up or down, up or down. The electron is not a one-dimensional wave. It's not even a two-dimensional wave. It's a three-dimensional wave. But this is where our model becomes kind of, hard to stomach, because what does a two-dimensional wave like? We don't have a lot of understanding of that, let alone what a three-dimensional wave looks like. So here, this is some salt on the top of a speaker. Now, a speaker creates sound waves. Sound waves behave slightly differently, but they have similar principles in terms of the way that they refract, the way that they can become constructive or deconstructive, depending on how they line up. And also, they have nodes, or n values, n equals 1, 2, 3, 4, different ways that they can be emitted or released, right? Our sound waves. And the speaker does this simply by vibrating. And so we can visualize the mode by watching our sand move as we change the frequency of the sound. So it sounds like it's pretty continuous, but you can also hear that there are certain sounds that are stronger and certain ones that are weaker, indicating that there aren't an infinite number of ways for this speaker to vibrate. And see, the sand is gathering in the spots where there's no motion, right? The motion moves the sand away or the salt away, and then it gathers in regions where there's no motion.
Why is it doing that?
Okay, so what's happening is this two-dimensional surface is vibrating. It's vibrating. And as it vibrates, the sand moves to the regions where there's no vibration.
So why does it shift like that?
It's shifting because that's the only way that it can vibrate to make that frequency that we're trying to hear. So notice how it stops making noise and then it starts making lots of noise when it finds a resonance, a way that it can vibrate and create that sound. Okay, so this goes on and on and on, and you get all sorts of different patterns. Okay, so what did we learn there? Well, that's trying to teach us a little bit about, what we call a two-dimensional standing wave. Now, a three-dimensional standing wave is a little more complex than that, and I don't really have a good model to kind of show it to you. We'll have some pictures that we can kind of think about, but the region, or that the shape that those electrons kind of are in can be described by wave functions or wave equations. Do you remember in math, sometimes you might have taken math, you can get the equation of a line. You can write down y equals mx squared, or we can write the equation of a circle, right? Or even the equation of an oval or a parabola, right? You can have equations of these, the regions where the electrons kind of reside, and so we can see their shape, and the wave function helps us do that. But we really just are going to kind of focus on some of the values that go into these wave functions. We're not going to talk about the wave function equations themselves, but there are some interesting values that we can use as tools to talk about the energy of the electrons and about the different electromagnetic energy that's released or absorbed upon interaction of matter or elements with that electromagnetic energy. Okay, so these are some what we call quantum numbers that we use as tools, and they are values that go into these wave functions. Now, we're not going to talk about or show wave functions. They're just complex math, but we're going to use quantum numbers to kind of describe electrons and their orbitals.
Why are we doing this?
Well, it seems complicated at first, but we'll see that it's not hard to remember, and after a while we'll be able to explain different phenomena. For example, we've never really talked about why an element like iron can have a +2 and a +3 charge, or an element like chromium can have lots of different kinds of charge states. We want to know why that is. Zinc is a transition metal, but it only has a +2 charge. I don't know if you realize that from homework problems, but it's an exception to the transition metals. So why is that? Well, understanding these quantum numbers will help us have an explanation for why we have various charge states like that. Okay? So next time we come back, we'll introduce and talk about these quantum numbers. See you later. Are you okay?
I got a headache.
Yeah, I understand. Okay, see you.